Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It gives me great pleasure to introduce Ari Gurfinkel, who was visiting from the Software Engineering Institute by CMU. And he's here all week until at least Thursday afternoon, maybe even Friday morning. So after the talk, or during the talk, asking questions, and after the talk, he sits, what was it, 3123 or 43, and you can grab Ari and ask him even more questions. Okay, go ahead.
Okay, thank you, Nikolai. So I'll talk about VINTA, which is a joint work with Alz Albergathi and Marcia Chechik. And then some of the work I'll talk about is also a joint work with Sagar Chaki, who works with me at the SCI, and Ely, who's also in Toronto with Marcia. Okay, I have to show this. So anything I say, there's no warranty on it. Okay, so my work is in automated software analysis. And I'm not going to spend any time motivating why this is important. So I'm assuming you're already motivated enough. So I'm just going to get directly to the point. So what I work on is this box called automated analysis. And from my perspective, the view of the world is very simple. You have a program and maybe some notion of correctness, maybe inside the program, maybe as a separate property. And you have to come up with one of two answers, either correct, maybe a proof of correctness, or incorrect, and maybe a counterexample. And from my perspective, there's sort of two ways to solve this problem, two big approaches. And one is called software model checking. It's been pioneered by a professor at Clark, among others. And abstract interpretation, which was pioneered by Kusot. So last year I was here and I was talking about UFO, which was sort of a model checking driven view of the program verification. And today I'll talk about VINTA, which is more or less the same story, but now from the abstract interpretation perspective. Okay? So the motivation that we had is sort of on one hand, abstract interpretation is the most scalable approach to program analysis. That's the one that scales to programs with millions of lines of code. But in practice, there is a price for that. It's very scalable because it's imprecise. And because it's imprecise, it has lots of false positives. And two other problems with it, it gives you no counterexamples and no refinement. So if it claims that there is a bug, there is no actual execution you can look at and say, oh yeah, I see what's going on. And there is no refinement. If you have a false positive, you have a false positive. That's it. So that's sort of the motivation we wanted to do. We wanted to go and reach into sort of a model checking view of the world where you have abstraction refinement and try and add it to an abstraction interpreter, to abstract interpreter. Okay. So what I'm going to do in the rest of the talk is I'll talk about numeric abstract interpretation. Does anybody here doesn't know what numeric abstract interpretation is? Great. Okay, and I'll go slowly over that part. So I'll just give you my view of what it looks like. And I'll talk about VINTA. So what did we do that's different, how it changes this picture. I'll talk about how it's implemented. And then sort of the biggest claim of fame of VINTA is that it did really well at the recent software verification competition. So instead of showing you how we did on some benchmarks that we've tried it, I'll talk about what it did in the competition and how much responsible it was for the performance of the tool. And I'll, if I have time, I'll talk a little bit about the secret sauce. So all of the things that went on top of the basic algorithm in order to make it competitive. And then finish with some of the current work that I'm doing. I'll try and make it informal. Please feel free and ask questions, so interrupt in the middle as I go. So numeric abstract interpretation. So what is it? The basic idea is that you restrict the set of facts that you're going to use when analyzing a program to something called an abstract domain. And you do all your reasoning inside the set of facts. So the thing to note here is that the abstract domain is a possible infinite set of predicates. So you have to deal somehow with that. But the predicates come from a fixed theory. So you know a priori all the shapes of the predicates. And you have some efficient way to do the abstract operations. So here are some examples of numeric abstract domains. So the first one is sort of the simplest one, is the sign domain, where for each variable you're going to keep track of whether it's positive, negative, or 0. So it's the only fact that you can express is in one of those things. The next one is a box and interval domain, where the only fact that you're allowed to say about each variable, what is it upper and lower bound. Then you can go down and have something like octagons, where you have where you can express for any two variables whether they're equal, not equal, or how far apart they are. And then for the most expressive numeric domain is polyhedra, which allows you to use any linear inequalities. Okay, so that's the first part. That's a domain. So let's see how it works. So this is going to be a small program, and we're going to run an abstract interpreter on it. So we're going to do an interval, a box domain here. So first, we'll go into a loop, and we'll ask, well, what do we know at this point in our abstract domain? And we know that y1 is between 3 and 4. We'll then go through these statements, and we'll say, well, what do we know after executing those statements? And we know that x1 is between 1 and 2, x2 is between 5 and 6, and y1 is still between 3 and 4. We then can go into another branch of this if statement, and again ask, what do we know here? We know that y2 is between 3 and 4. It just comes from this if condition. Apply those operations, and we know that x1 is between 1 and 2, x2 is between 5 and 6. Okay. Now we have to do a join at this point. So we have to say, when we come to this point, what do we know? What is the set of facts that we know? And we can only express them as a conjunction of upper and lower bounds. So what we know is that x1 is between 1 and 2, because that's the same thing here. And x2 is between 5 and 6. And we don't know anything about y1, and we don't know anything about y2. Right? Because in one branch of the conditional, we know that y1 is bounded, but in another branch, we know nothing about it. And the opposite is true about y2. So when we come to a join point, we just forget y1, and that's it. Okay? And so in this point, we check whether this implies our assertion. It does, and we're done. Okay? So pretty straightforward. Now let's do another example. So what happens? This was the first example was really simple. There were no loops. We just propagated things, and we're done. So now we'll have a loop. So we're going to do the same thing. Initially, we know that x is 0. As we go into a loop, well, x is 0 and also less than 1,000. As we increment, now x is 1. We come back to the loop. We have to join. So we knew that x was 0. The second time we come, x is 1. We can express it as this interval constraint, x is between 0 and 1. And we can continue and do this again and again and again. And so what's the problem here? Well, the problem, it may take quite a long time or even forever to just go and sort of execute the program like this. And so at this point, what the abstract interpretation typically does is pulls the rabbit out of a hat. It's called widening. It says somehow, let's guess where this is going. So here, for example, we saw that x was increasing, and we decided to guess that it's going to increase forever. And then we know that we only enter a loop when x is bounded by 1,000. So let's use that as an upper bound. And we go through another execution of abstract interpretation, now carrying this constraint. So we know if we enter a loop, x has to be less than 1,000. When we increment by 1, it's at most 1,000. And now we know that we've converged. There's no new states being generated. So we found an inductive invariant. We come to our assertion, and it's satisfied, and we're good. Okay. So if we want to look at an abstract interpretation sort of from operational perspective, then it really gives us this interface. We have a notion of an abstract domain. It knows about a set of variables that we keep track of. There's a set of abstract elements, which is how we represent our abstract values. There's expressions, which we use to represent program states, and statements. And the functions that we have from an abstract domain is we have an abstraction function to go from expressions to elements of abstract domain. We have a concretization function so that we can say what the result is, how to understand an abstract value. We have an order, so that we know what does it mean that we've converged, no more new states. So what abstract set is subset of another abstract set. And we have an abstract post, an abstract transformer. This is a function that takes a concrete statement, like x gets x plus 1, and changes it into a statement that operates on abstract values. That takes an upper and lower bound and tells you how plus 1 transforms an upper and lower bound. And then we have the meet, which is intersection, join, which is union, and widen, which is our rabbit to go with this. So here's an example of how an abstract domain looks like in the case of a box abstract domain. So our expressions are all statements of the form x with an upper and lower bound. Our abstraction gives us an abstract element, which will be just a tuple representing the lower and upper bound of a value. Our concretization takes us back. The operations are very straightforward. If we want to take an intersection of two intervals, then we just take the max of their lower bounds and the mean of their upper bounds. If we want to take a union of two intervals, then we take the mean of their mins and max of their maxes. And if we want to do an abstract transformer, in most cases, it's just you apply the operation to the lower and upper bound. And that's it. Note that here we have some imprecision. Right? So when we do a join, if, for example, we have an interval 1, 3 and an interval 7, 12, a join of them is the interval 1 to 12. There's some over-approximation. We added more things which were not actually part of that interval. And this is where the sort of scalability of the abstract interpretation is. Because we restrict ourselves to very simple elements, the abstract domain, we can manipulate them very efficiently, but we pay the price. We can't express everything we want to express. So let's see how this influences the result. So we're going to run, again, the abstract interpreter in this program, and it's going to fail some. So at first, we assume that I is either 1 or 2. We can represent that as I is between 1 and 2. We're going to first branch of an if. We know I is 1 at this point. X gets I, so x1 is 1 at this point. The other branch, I is 2. x2 is minus 4. Got that? And now we have to do a join. And as we do a join, we now get we'll lose some of our precision. Because we know on this branch of the if statement, we had something about x1. On this branch of an if, we had something about x2. When we join, we know nothing about x1 or x2, because we don't know which way we got to the join point. And so we'll only learn that I is between 1 and 2, because I was 1 here and 2 here. And now as we go into our second if, we get y is 1 and y is 2. So both of the things are reachable. But we don't know anything about x1 or x2, so we're going to create a false positive. Right? We're going to say that these assertions, as far as we know, abstractly, we cannot prove that they are unreachable. But if you go through the program, they aren't. So that's a false positive. Okay? So that's the situation that we want to fix. So when the solution that we're proposing is something which we call VINTA, which wraps an abstract interpretation into an abstraction refinement cycle. So the high level is really a very simple idea. You start with a program, and you run an abstract interpreter. Well, what an abstract interpreter will do, it will compute to you some inductive invariant. You check whether this inductive invariant happens to be safe. If it is, you're done. The abstract interpreter proven that your program is correct, and you're done. On the other hand, if the invariant is not safe, then you know that the abstract interpreter looked at part of your program and found some counterexample. So you switch to the refinement phase, and you check all of the execution that the abstract interpreter has looked at, and check whether they have a concrete counterexample. If they do, then you terminate and you say the program is unsafe and you have your counterexample. Otherwise, use interpolation to figure out what the facts have the abstract interpreter forgotten that a part of the bounded program that it had looked at that makes it safe. And then you use these facts to strengthen the state of the abstract interpreter. So you have an inductive invariant here that's not safe. You come here, you check it, and you find out that there is no counterexample. And you come back, and now you have something which is safe. An error state is unreachable, but no longer inductive. And then you restart an abstract interpreter from that point to compute the next fixed point, to add more reachable states until the set becomes inductive again. And then when it's inductive, you check if it's safe, you're done. If it's not safe, you go back and you possibly strengthen it again. And you keep iterating back and forth. Okay? Now, there's several novel things we had to do in order to get this to actually work. And so when I'm listing here sort of what's novel from the abstract interpretation perspective and what's novel from the refinement perspective. So from the abstract interpretation perspective, one novel element is that we use cut point graphs instead of control flow graphs. And what that means is that we compute an abstract value for every loop head as opposed to for every basic block, as opposed to every statement. It also means that when we say that a program makes a step, it's a very large step. It's basically some kind of loop-free program fragment, as opposed to a single thing like x gets x plus 1, which makes our abstract interpretation step a little bit more complicated, but it can also be a lot more precise because it can be exact on those intermediate steps. Now, the second thing that we do is that instead of just computing what's reachable at any program location, we compute an unfolding of a control flow graph. Okay, so if we come to a loop multiple times, we keep multiple copies of it as sort of an unrolling of a control flow graph that the abstract interpreter had looked at. And that has two side effects. One is that you know everything that abstract interpreter has explored. This unfolding at the end is sort of the bounded program that the abstract interpreter is basing its result on. And that's what will be used in refinement. And second, it means that we always compute disjunctive invariants. Okay? So what I've showed you before, the box domain, for example, it will compute an upper and lower bound for every variable at every location. But because we unfold the control flow graph and because the location that, say, is part of a loop will appear multiple times in a graph, we automatically compute a disjunctive invariant because the invariant for that location will be the union of the labels at all locations corresponding to it. Okay, so this.
You map. Do you also keep track of the number of the iteration that was used for that disjunct, or?
So I'll show you in the next slide how it looks like. So this is sort of a side effect of keeping an unfolding, because we keep a whole unfolding, you could get all of this information from it. Right? So it's we don't need to keep as a separate number, say, in what iteration was this label computed. It's simply an annotation of an unfolding graph. And then in this graph, given each loop, say, how far it is from the initial state. But one of the side effects of this is sort of what we do, given any abstract domain. And here, we lift it into disjunctions. We lift it into a power set domain. And so we had to fiddle and get the widening to work correctly. And so we ended up sort of creating a different widening than any of the existing ones that's tightly coupled with the exploration strategy.
And when you say disjunctive invariance, is there like a fixed bound on how many disjuncts? And if there's no bound, is that delegate to widening to?
Well,
what makes it converge?
What makes it converge?
So disjunction. You trade disjuncts for counterexamples. Is the typical.
Yes. So I don't have slides for it. It's a little bit trickier, but I don't think we put a bound on number of disjuncts. But at the same time, we can prove that there is some progress following that. What's going to happen is that you have multiple disjuncts, but you're going to widen, whenever you want to add a new element to this set of disjuncts, you're going to widen it with one of the existing elements. And then what you have to show is that you get this set of disjuncts growing, but at the same time, there's always a path where at least one of the disjuncts is being constantly widened.
Okay.
And therefore, that whole chain can never go for it.
So widening gives you the convergence?
Widening gives us the convergence, but whenever you do power set widening, you always have to be careful because you may end up that the number of disjuncts grows. Also, each chain for each disjunct is finite. And then you would still not converge.
So in some sense, you rely on the refinement to make it somehow terminate at some point, right?
Well, the abstract interpretation has to terminate itself, and then
Sure, yeah.
the refinement will push back on it.
But you could, yeah.
Okay, so let me wave my hand and say it does converge, but I don't have. I actually don't have slides on widening. I haven't. Didn't think that would be that interesting here. But if you want to ask me later, I can explain how it works. And then from the refinement perspective, what we do that's interesting is we use an SMT solver to check for whether counterexamples is feasible, which is fairly novel in case of abstract interpretation. And then we use this concept of DAG interpolation for refinement, which I'll go more about. And what's interesting in this particular work is that this interpolation procedure is sort of guided by abstract interpretation. They play together in order to figure out how to refine. And the overall effect is quite interesting. On one hand, the abstract interpretation is all about throwing away constraints in order to get convergence. And then the refinement part ends up adding constraints that were thrown that are actually necessary to prove that certain counterexamples are infeasible. So let me just illustrate how this works on an example. So I'm going to take this program and I'm going to take it through different steps and show how they work. So a few things to know. When we explore the program, we use weak topological order, which means we always go for inner loops and wait until they converge, until we go out. We're going to use an abstract domain of intervals in here and look around that the side effect of our abstract analysis will be this labeled unfolding. So we start abstract interpretation the usual way. 1 means this control node 1. Initially, it's labeled with true. Everything is reachable initially. We make one step. We figure out that x is 10. We make another step. We figure out that x is less than or equal than 10. So we did a little bit of widening here. And we went from 8 to 10. Then we go one more through the loop. If x was less than 10 and we subtract 2, it remains less than 10. So we got to converge. Right? We don't get any more reachable states. We're done with this loop. We now look what's reachable other than the loop. So we'll get the 3 edges to location 3. And right now we can prove that when you get here, x is less than or equal than 10. Therefore, this if condition is possible. You go in, x is 9, and you hit an error. Okay? So now we're going to raise the alarm. So this is end of our abstract interpretation phase. So we run the abstract interpretation phase as usual. But look what we get as a side effect is this unrolling. Right? So instead of, for example, maintaining that x is less than 10 for location 2, we have this full unfolding. And we know that our invariant now at location 2 is a disjunction of those labels. Okay? Does that answer your question?
The first question, yeah.
So that's how it's going. So now, when we have an alarm, we want to check whether this alarm is spurious or not. And basically, what we're checking is whether in this bounded program, this location is reachable. Okay? And to do that, we switch to an SMT, just generating a verification condition for this bounded problem and checking it using SMT. So we start with our unfolding. We forget about our abstract interpretation labels. And we start generating a verification condition. For each edge here, we'll just assign what the action of that edge is. And then we build a control flow encoding where for each node in the control flow graph, we'll add a Boolean variable and basically specify that if you happen to be in one location, then in order to get to another location, the edge condition has to be true. Right? And the same for each individual node. So this encoding is really straightforward in the sense that it's linear in the size of this unfolding. So it's very easy to generate. And then we give it to an SMT solver to check if there is a counterexample. Okay? And there's 2 answers. Either there is a counterexample, and then the abstract interpretation phase gave us a good alarm. We can produce this counterexample. Or the result is no, there is no counterexample, and we need to do some kind of refinement. Okay? So to do refinement, we're using Craig interpolation. And I know, are people here familiar with Craig interpolation? Or see somebody smiling? And so Craig interpolation is an old theorem that says something really simple. It says, roughly, if you have A that implies B, then there exists an I in the middle, such that A implies I, and I implies B, and I is in the language which is common to A and B. Okay? And here I'm stating it sort of in a slightly different way, where I'm saying, well, A implies not B, just because that's a more convenient way for software model checking application. So Craig theorem has been around for a long time, and we also know that it's quite operational. It's quite easy to construct the Craig interpolant, given, say, a SAT proof or an SMT proof, given a resolution proof. And in model checking, it's used to over-approximate the set of reachable states. But let's see how we want to use it here for refinement. So this statement is not quite good enough for us, because it talks only about two parts. We have some prefix and some suffix, and we can compute what's reachable by a prefix before a suffix. But in our case, we don't have simple two parts, A and B. And we don't even have a pass. We have a direct acyclic graph that represents our unfolding. And so the problem that we want to solve is something that we called a DAG interpolation problem. And roughly speaking, it says something like this. It says, given a graph, a DAG, where each edge of a graph is annotated by a formula, so formulas pi in here, such that on any path, a conjunction of the pi formulas is unsatisfiable. What we're looking for is the set of these orange labels I, such that each label is an interpolant between every prefix and every suffix. And every label that together with any edge implies the next label. Okay. So here's an example. So for example, I2 has to be an interpolant between pi 1 and pi 8 because of this. But also it has to be an interpolant between pi 1 and pi 2, pi 3, pi 6, and pi 7. Okay. And the second condition is that, for example, I2 and pi 2 has to imply I3, and I2 and pi A has to imply I7, and so on. So if you think about these conditions carefully, then you'll see really what we're looking for, sort of a Hoare-style proof of correctness of this program. Right? We're looking for intermediate states I1 to In, such that the initial state is true, the final state is false, and any state together with any statement implies the next state. Now the question is, how do we compute such a thing? And there are multiple ways to do so. So one way is to just cast this as sort of a horn problem, where you treat each individual i's as an unknown predicate, and you just pose those restrictions that you want as a horn satisfiability problem. But another way is to turn it into an interpolation problem, into a linear interpolation problem, that you encode this whole program just as a normal verification condition, give it to a SAT solver, get a result, and then mine the result, this proof, for the labels. And this is... isn't
it fair to say that the linear interpolation methods predates this view, this other view?
Right, the linear interpolation methods predate. So the linear interpolation method is in 1957.
Or I mean, the tools that you're using also predates.
Right, and the tools that we're using predate the horn formulation. Yeah. At least in SMT world. So the way we actually solve this problem is sort of in this very simple way. We translate this whole problem into a sequential interpolation problem that's already supported by existing tools. And the idea is sort of quite simple. At first, we take this graph and we build a verification condition. And we realize that the verification condition has this form where you have assertions for different locations in the control flow graph. And you can order those assertions in a topological order. So you have a linear sequence that each element further in the sequence means you deeper inside the graph. Okay? We then can compute a sequence interpolant for each, for the cut between each location and the following locations. So sort of cutting the graph in different places. And then this will give us almost the result that we want, except if you follow the definition of interpolation, you may have variables which are out of scope at a given location. If you have two nodes of a graph which are siblings of one another, then variables that are only available for one sibling may appear in an interpolant for the other. Okay? And that's a problem for us because at the end of the day, you want to get something that's maybe inductive, and so you don't want to have any free variables, any out-of-scope variables in your expressions. Otherwise, they'll have to be quantified out, and you have to deal with quantified formulas. And so we go through this cleaning process to somehow get rid of them. So that's the price we pay for using a sequential interpolation method. So we get an easy encoding into it, but the output is not quite what we want, and we have to spend some time on this cleaning phase. And actually, we spent quite a while playing with various versions of this. Original one used quantifier elimination during cleaning when all heuristics failed. We have a new encoding that now can do clean completely using projection and no quantifier elimination at all. And I'm looking at various other ways using, for example, the Horn procedure that 3 has. Boss has to solve this whole problem at once, and also to just break it to solve just the cleaning part of that problem. So that's that. So let's go back to our running example and see where we are. So what DAG interpolation will give us is we have this graph. We know that the result is unsatisfiable. So when we crank the DAG interpolation handle, we're going to get this I1 to I3 in this case, where I1 will be true because everything is reachable here, and I3 will be false because in this particular example, error is unreachable. And this is true for every edge. Okay? So now we could have taken these I labels and used them to strengthen the result of abstract interpretation. Right? We can go to every abstract label and add those labels to it and say that's also true, and that prevents an error from happening. Okay? But there's one catch here. Sort of, by the time we got to this point, we already forgot anything that abstract interpreter has computed. And so we end up redoing a lot of the work that it has done. And we found this approach to be really inefficient when you get larger and larger unfoldings generated by the abstract interpreter. So what we really want to know is we want to see, well, the abstract interpreter already found some bound on the reachable states. What we really want to know is what else we have to add to that bound in order for the program to be safe. Okay, so we only want to know how to sort of help the abstract interpreter as opposed to redo its job. And the solution is quite simple. We simply say, well, then what it means that what we want is sort of a restricted DAG interpolant. We want to take our program, take the result of abstract interpretation, and just say, well, let the program assume them. Okay? So at every program step, we can just add an assertion and say, well, if an abstract interpreter said X has this bound, just assume that X always has this bound at this particular point. That's not going to change our program because we know that the abstract interpreter computed the set of the over approximation. But it will change what a solver has to discover. Because those facts are already there, they're already available, and they can be used. Okay? And then the solution to this problem, the solution to the interpolation problem will be, well, what other facts do I need to add in order for this problem to be unsatisfiable?
Is there a step that takes these I's and conditions them to the AI domain that is being used? Because these I's may not be discovered in the same form that the domain of AI is.
Yes.
So is there a step that conditions them, and will that lead to, I don't know, I mean,
yes.
Maybe it will lead to loss of
yes.
precision of
yes.
what you found in the...
So this is actually some of the things that we're looking at right now. I have a couple of slides at the end to address this question. So yes, you're absolutely right. So the question is that these labels may be in arbitrary form, arbitrary SMT formulas. Whereas for an abstract domain, we need something like, say, a conjunction of linear inequalities, a convex hull of some sort. So how do you go from one to another? And the answer in practice, how do we go between one and the other? We just have a very simple heuristic to get something in an abstract domain that over-approximates each label. But really solving this problem for real is quite difficult, and we're working a little bit on it.
Simple question on the slide is that when you conjoin AIs to the edges on the right, doesn't it correspond to just conjoining AI to preconditioned locations? I'm wondering why you did not just add AI as a conjunction to the location.
Here?
Yeah, next to TIJ.
Well, that's exactly what we do. Except you're thinking about it in terms of a horn presentation, so you're thinking I's uninterpreted predicates, and this is given to you. Whereas I'm saying this is what's given to me, and I produce I's, which is the solutions to my horn problem, and it satisfies this predicate.
But it satisfies a...
yes, it satisfies...
oh yeah, okay, there we go. Okay, thank you.
Yes. But this is where the problem statement is. This is a statement about the result. Whereas in a horn formulation, you state that you want the result that satisfies this, and the solver gives you the result. Yes. But the point is that the output that you get now, you don't get a DAG interpolant, you don't get something that's good enough on its own, but something that's good enough together with abstract interpretation label. Okay? So if we go back to our running example, and we would have run this whole process here, this is what we get. We have the blue labels, which is what the abstract interpreter has computed. And we have this orange labels, well, the non-blue labels, which is what we've computed by the interpolation. And so what you have to note here is that, for example, this label happens to be true, which basically says the abstract interpreter already knows enough about this particular location because it knows that x is 10. I don't need to add any more. And here I want to add that x is not just less than 10, but it's also 8. And here I want to add that x is not just less than 10, but it's also 6. And so now, once we've strengthened the result, so we still have sort of a reasonable abstract interpretation state. And in this case, all of the constraints happen to be inside the abstract domain. But one thing is broken. And the one thing that's broken is that this result is now safe, but is no longer inductive. So we know that because we know that this edge is no longer true. This relationship that the set of reachable states here is a subset of the reachable states here is no longer true. X is 6 is not a subset of x is 8. And so we can restart the abstract interpretation right from this point. Okay? So this is where we need this ability to take this label, convert it back to an abstract domain, and then we can run our abstract interpreter again. Here it will find out that, well, if x was equal to 6 and we run one step, it's less than 6, we converge. We come here, it's less than 6, and x is never 9. That's it. Okay. So just to give you a high-level overview of what's happening here, is we run an abstract interpretation, but at the same time we keep our unfolding, we keep the bounded program that the abstract interpreter has given us, and we get our blue labels. If an error is reachable, we go to refinement phase, which basically asks, give me a horse-style proof why you think this bounded program is safe. That's our orange labels. We then mix the orange labels with the blue labels, which now proves that this bounded part is safe. So we have something that's safe, but is no longer inductive. And if it's not inductive, it means that there are some loops which are not covered, some loops where we haven't explored all the reachable states. We find out those loops, and we restart the abstract interpretation from this point. That's it. So this is implemented in a tool which we call UFO. It's available here with source, so feel free to look through it, run it, try it, and contact me if you have any sort of questions or need help. But this is the architecture of the tool. We have this big front end, which I'll talk more about, that basically goes from C into our intermediate representation via LLVM. And then the heart of the tool is this arc constructor that builds this graph, which we call an abstract reachability graph. And you can control it by giving an expansion strategy, how you want to expand the graph, what abstract domain you want to use, and how exactly you want to refine. So there's lots of choices on how to apply DAG interpolation. It uses 2 SMT solvers. It uses Z3 for almost for everything, and it uses masstat for interpolation. Okay, so are there any questions so far? Yeah.
All of your examples were type safe, very simple. And I was expecting to hear that no, this only works on type safe languages, but you said C. How do you deal with type unsafe?
I pretend to not know about it.
Okay.
So we deal. Okay. So this has to go about the software verification competition. So all examples I've shown you were small, just to fit on the slide, but I'm claiming this works because of the software verification competition, not because of the small example. And now one of the so okay, let me tell you a little bit about the competition and answer that. I mean, that's a very serious question, and I don't have any good answers. So the software verification competition.
So I'm trying to figure out how applicable it is.
Okay, so let me. So the software verification competition started in 2012, and so this year was the second year. It's held as part of ITOPS and collocated with TACAST conference in ITOPS. Its goal is to provide the snapshot of state-of-the-art in software verification tools. It had quite a few participants and quite a few benchmarks. So one of the issues with, this, with any competition like this, so the decision was made to use C as the language, so that the tools actually support some realistic language, not a toy, not an intermediate language. But the problem is that we don't have formal semantics of C. I mean, even before type safety, even just settling on the formal semantics of the language is impossible. And here the decision was made that we'll just use the semantics which are reasonable for the benchmarks to which all of the participants agree. And the way it works is that there's a large collection of programs. Everybody runs their tool. They get different, the benchmarks are marked whether they should have an error or don't have an error. Everybody runs their tool, decides on the results, and if people happen to disagree, there's a discussion and we decide whether the benchmark is kept, removed, or what to do with this particular case. So in that sense, the answer is sort of very pragmatic and driven by the benchmarks, as opposed to trying to answer a more general question. The way
type safety checks as error labels.
Well, you could, but that's so the way we actually do. We live inside LLVM. We let LLVM get to an intermediate representation, at which point we only work at the level of numeric registers that LLVM provides. So LLVM compiles the program down to infinitely many numeric registers and memory. We treat memory as completely non-deterministic, and numeric registers. That's what we analyze. So I can give you a formal semantics of what we verify with respect to that, but tying it back to C is quite difficult. And
so do you not handle pointers at all?
We don't handle pointers at all. But that's it's not to say that these programs don't have pointers, that we don't handle programs with pointers. That is to say that pointers, a lot of the pointers are removed at the pre-processing level when the program is compiled down to registers. By LLVM and by our passes. So if you can prove that a certain location is not LS, then it will be compiled down to a register. And then all the pointer references will be updated. So these programs, so the benchmarks consist of a large collection of C programs ranging from sort of things that people traditionally use for their tools to a big set of Linux device drivers. So they know toy programs, they don't use toy part of a language, they do whatever they want. But most of the properties that we want to prove are the kinds that don't really depend on deep pointer reasoning or type safety or things like that.
You still have some kind of heap domain for the abstract interpretation, right? So, is that sound in a sense? Or
Yeah, it is sound because I assume that heap is completely non-deterministic. So if you write something to heap and then read something from a heap, you get a non-deterministic value. So that's sound. It's just maybe not precise for anything interesting that you want to say. Put something in a heap, I build a linked list, and then I want to navigate through it. And the tool will just tell you, you end up in an arbitrary place.
Okay, so you get aliases which might not be aliases, for instance.
Right. But the reason why this works is that the front end takes care of lowering a lot of the pointer reasoning. Any sort of shallow pointer reasoning gets lowered into registers by the front end.
So at a high level, so there are model checkers who do similar thing, right, which refine the predicates based on counterexamples lazily. So at a high level, what is the advantage that adding abstract interpretation to this is giving? It's more precise somehow, it converges faster because of widening?
It wins competition.
It wins competition. It wins competition. That's Nikolai's answer.
You blast and
so the tools that we're participating, so the ones that are in bold are the tools that somehow solve the same problems as our tool solves. The tool is called UFO. There's 3 tools which are sort of in a different lead. CSAC and Shredder do concurrency, and only concurrency, and we don't, so we never compared with them. And Predator does sort of deep memory things, which again, we haven't competed on those benchmarks. But for all other benchmarks, UFO seems to perform a lot better.
Why is my question?
Well, it's hard to tease out why, like if you pick a particular point and you say, is this particular thing important? I can say, yes, if I turn it off, it doesn't perform as well. But if you just take this particular thing and remove everything else, you don't know. So why is abstract interpretation important? Well, because it can discover facts out of an infinite domain of predicates. If you use predicate abstraction, you may get stuck trying to figure out what is the right predicates. Whereas here you start with an infinite set of restricted predicates. And you use widening to find out what is a good set. But widening can overshoot, and so you use sort of the same refinement techniques to bring you back into a safe region. Any more questions? Okay, so this is how the competition was run. So the way the scoring was done, you get points for solving things correctly, you get negative points for solving things incorrectly, and it was deemed that finding a counterexample is easier than proving something correct. So you get more points if you proved something correct when it is correct, and you get more negative points if you prove something correct which isn't. And the distinction in these numbers was partly influenced by the previous year, where a toolset would do bounded model checking, would look only in few executions, would really win everything because they would look at a few executions and say the program is safe, and the distribution of benchmarks was such that if you have an error, it's a very shallow error. And so those tools would constantly win. Now this year, there's many more benchmarks, and that's no longer true, but also the scoring was changed so that simply guessing things would penalize you more. Okay? So, well, that's our the outcome of this. So we've participated in 4 categories, which is control flow integers, which has all sorts of the traditional benchmarks used by software model checkers. And then product lines, which comes from Dirk Baer, some set of examples where there's the same program but different configurations of it. Device drivers, which come from Linux device driver verification project. And System C, which is System C programs converted to C with a scheduler. So System C is a hardware description language that describes concurrent systems. And so in all of those cases, the tool performed much better than just predicate abstraction by itself. And the abstract domains were sort of crucial to this. So if you look at the benchmarks, we'll see if you want to find that a bug, then it seems to be really good to use VINTA with a box abstract domain. And the intuition here is that the box domain is not very precise, but if it can tell you that you need to unroll a loop, that loop is easy to know that it's safe for a small bound. And so this domain seems to be really good at figuring out how much to unroll the system so that a bounded model checker will find a counterexample. And then we have VINTA with a boxes domain, which I'll talk about in a second, which is a domain that allows to have disjunction in addition to intervals. And that domain very closely mimics the typical predicates that a software model checker finds, except it has all of them at once. And it seems to be really good at proving safety. Okay. So let's see if I can bring up the results. No, thank you.
You want some kids?
I want some kids, that's true. So this is, if you want to go to that link, you'll see lots of details about who did what. This is our UFO column. I know I want to go down into numbers, but if you're interested, you could go and you could click on all of the numbers and it will give you a comparison of tools and draw you graphs. And you can try and tease out what's the difference between different techniques. Yes, you can get, well, so yes, actually we got a negative score overall, and we didn't quite realize what this category was. So the idea for the overall category, we thought it was sort of the addition of all the other things. But in fact, the overall category was all the tools around and all the benchmarks, even the ones that they don't know anything about. And if the tool gives you a wrong answer as opposed to unknown, it's penalized. But you are allowed, which we didn't know, to check the benchmarks. For example, if the question was about memory, you could just say unknown, whereas we didn't. And so that's what separates this column. Okay. So, so let me tell you more about sort of what else. So VINTA was, I think, was the main reason why we did so well in the competition. But there were a number of other things that really influenced, and those things which we don't typically publish. They're like small things that end up making a big difference. So the secret sauce, the important things were the front end. I'll tell you more about it. Combining with abstract interpretation. The box's abstract domain, which I'll again talk about in a second. The stability of computing DAG interpolation. So computing a solution to this whole problem at once, as opposed to doing it like pass at a time or lazily or in any other way. And then at the end of the day, we do run a lot of things in parallel. So so we don't have to worry about which particular setting is the best one. So the front end is something that in principle is really, really simple, but in practice it's extremely messy. So what we ended up happening is it's really a huge mess. So there's a seal pass that goes through the code and normalizes it. And this is basically where I try to fight against the software competition semantics, because their semantics have nothing to do with, say, what a compiler thinks legal C should do. For example, in a software competition, it was assumed if a variable is uninitialized, it can have an arbitrary value. When a compiler sees an uninitialized variable, it says it means it's undefined. And therefore, it's legal for it to do anything. So if you have a branch on an undefined variable, you could pick the easiest path you want to take and optimize the other path away. So there's a seal path that sort of tries to do this at a syntactic level to try and fix all of those things. For example, we add just calls to non-deterministic functions to initialize every variable. Then there's a LLVM GCC path, which uses GCC to take the benchmarks and convert them into LLVM land. Then there's a LLVM optimizer based on an old version of LLVM that has a good optimizer but not too good that we use in order to simplify memory and do all of those things. And the problem here, if you switch to a new version of LLVM, the optimizations are too smart. And so again, you get into this clash that so for example, in the competition, it was assumed that if you get a non-deterministic integer using a non-det-int function, and you cast it into long, you get a non-deterministic long. Well, what a compiler will tell you, no, you still get a non-deterministic int, and the top bits of this long will be 0. New LLVM knows about this and simplifies based on that. Older LLVMs didn't. So after you get through all of this, you could look at what happens to the benchmarks. And this is quite interesting that out of 1,592 safe benchmarks, the front end happens to prove 1,321 of them. So many of them are just simple things that you could do by constant propagation and simple simplifications. For the unsafe examples, okay, there's fewer of them that the front end can remove. Okay. So a big part of this is just having a really good front end. Now the second thing was this boxes abstract domain, which is I think unique to what to our tool. And the idea here is to say that in most cases, when we think about programs where software model checker did well, we want to find an invariant that's not a convex hull. It's not an upper and lower bound of every variable, but it's more of a disjunction of such things. And so you'd want an abstract domain that's not a single box, not a single min-max, but rather a bunch of such boxes. Well, if you start thinking about it, then okay, it's easy to see what this domain is, but the difficulty is how do you maintain it? How do you represent this as a formula so it doesn't blow up? And the solution that we're using is using decision diagrams. So a while back, we've extended decision diagrams to linear arithmetic. So that's the decision diagrams where each node, in addition to having the true and false child, is labeled by a linear arithmetic formula. And then the diagram knows about it and does simplifications based on that. And the boxes domain is basically uses this data structure where each node represents a single min-max constraint. The interesting thing about this representation is that it's canonical for this domain. So it behaves virtually like BDDs and can be implemented really efficiently and lets you compactly represent those things. Okay. And then finally, we run everything in parallel. So we looked at various settings that the algorithm has using an abstract interpretation, using predicate abstraction, using different forms of refinement. And we couldn't find out any sort of best strategy. Since we were running out of time and the competition machine had 8 cores, we figured out we can run 8 different things in parallel and see what happens. And so this is what we ended up with. So there's a whole bunch of different combinations. So for example, this one does uses a lot of LLVM optimizations, uses a boxes abstract domain, and uses very non-aggressive widening. So it lets you go deep into the loops, but it's run for a very short time. So that's really good for cases where there's a couple of iterations of a loop, maybe 10 or so, that you have to get through. And the boxes domain can keep track of the state really precisely, and then you converge. But if you don't, then that's probably a bad strategy. And so if you see all of them are sort of this mix, use either a strong abstract domain or a weak abstract domain, and try and decide whether to run for a short time or for a longer time. Okay. So to conclude, more or less, this is where VINTA came from. This is VINTA's family. We started a while back with an algorithm called Whale, which was using interpolation to try and reason about recursive programs. We've sort of abandoned that work because we didn't have any good benchmarks to tune this algorithm in. And then we switched to the competition benchmarks. We first developed this UFO algorithm that eventually became our framework in which we do our development that introduced this concept of DAG interpolation and combining predicate abstraction with interpolation-based verification. And so VINTA pushed it a little bit further by adding abstract interpretation components. And the difference, the difference between these two conceptually is quite similar work. But in the details, there's quite a lot of difference. So we had to really work out how the widening would work, how to interface with the abstract interpreter. And the abstract interpreter really put a lot of stress on our DAG interpolation component. We really had to tune it a lot more. Just because here's the abstract interpreter would go much deeper into any loop than the predicate abstraction would. Okay. Well, are there any more questions or? So if not, I'll just want to talk about some of the current work and just maybe get your opinion maybe offline. So one of the problems that was that you actually asked is this question of what we call a symbolic abstraction. How do you build an abstract domain on top of an SMT solver? Or how do you go from an SMT formula into an abstract domain representation? And this is something that I'm working with actually Ely is the main student working on this, but it's a work together with Aus, Zach, and Marcia. So here's the statement of a problem. So VINTA wants an abstraction function, which basically an alpha that takes an SMT formula, say over linear arithmetic, to make it simple, and gives you a result in an abstract domain. Maybe a conjunction of linear inequalities, maybe a conjunction of min-max constraints. And if you think about it for a bit, implementing it is really an optimization problem. So you could look at it in this way. So formally, we have a quantifier free linear arithmetic formula phi. We have a bunch of terms, t1 to tk. And what we want to know is we want to find values for min I and max I, such that phi implies a conjunction of those bounds. And we want min and max to be the tightest possible. Right? And this would be a value in the abstract domain. This would be a value in the abstract domain of box. But really, it's more general because t can be arbitrary term. Right? And of course, without loss of generality, we can say, well, since phi is an SMT formula, it's enough for t to be a variable. If we want to make a term, we'll just add a new variable to phi. There is a naive solution, which is convert phi into DNF, take a disjunct, and then optimize using either simplex or Fourier-Motzkin, and then go on to the next disjunct. Okay? But that doesn't, at least the very naive version doesn't scale. And the problem here is that typically what we want a phi to be is really a bunch of loop-free executions of a program. So taking a DNF is quite large. So this is the solution that we've been playing with. It seems to be fairly effective. So in a nutshell, we want to do something really simple. We want to successively under-approximating phi by enumerating its models. But the problem is that if phi happens to be unbounded, if it's not a polytope, then if we just enumerate the models, we may go forever into some unbounded region. And so what we try to do is opportunistically check by basically shooting an array into a direction, whether it happens to be unbounded. So this is how it looks like on an example. So say we have this is our phi, this particular shape, and we're going to start under approximating. So we're going to give this phi to an SMT solver and ask for a model. And we may get a point in here. Then we can ask for another model, and we're optimizing x and y. So we'll ask for a model where x increases, and we can always ask for a model that's more on the faces of this polytope, right? By just taking a term corresponding to any of the faces and saying, find me a solution on it. So the next solution could be here. We ask for a bigger solution. Okay, so before asking for a bigger solution, this is what we're going to use in order to decide whether something is unbounded. So we have this fact that if you happen to have 2 points, P1 and P2, where x is increasing, so there's a ray through P1 and P2, and they happen to be in the same hyperplanes of phi, and there isn't P3 that on which x increases, but that's not on more hyperplanes than P3, than P2, then this direction is unbounded. So here, for example, if I look into this direction, I have this point. I have more points where x increases, but I have this point that lies on more hyperplanes. Right? It lies on the second hyperplane. So so right now I can't conclude whether the x direction is unbounded. I ask for another point where x is bigger. I'll get a point here. Well, now I know that the only way for x to be bounded, if there is another point on this hyperplane that intersects some other hyperplane. Right? I can check for that. I can have the equations follow the hyperplanes. I can just check. Does there exist a value where x is bigger? Yes. And that there exists a value where x is bigger that intersects one more hyperplane. And if the answer is no, then I know I have this whole direction. Right? And once I've got this, I now go and look for other values for x. So maybe I get lucky and I ask for the lower value of x, and I'll get here. That also happens to be a lower value for y. There isn't one. I ask for a higher value for y. Maybe I'm lucky and I get here. And now I have my, my convex hull. So that's our current solution. Okay, but looking for opinions of how to make it better. So one sort of limitations here is that when we get this point, we don't have any control. It seems like if we're using an external simplex, we could always get a point which maximizes x, for example, in a given polytope. But when we use an SMT solver, the interface we have now, we just ask for a point. And then we ask for another point in a completely separate query, as opposed to trying to say, well, give me a point, and then try and find another point in the polytope you're already in that maximizes that direction. That's it.
Cool. You're done with the talk?
Yes.
Oh, okay. Well, thank you.